Hello, this is Daryl Korn, and this is my walkthrough for homework 3. So let's get into it. All right. So first, I have my script for my simple RNN models. Um, we bring in the Kaggle data here, and then here we start transforming our data. So we have our one-hot encoding for our dependent variables right here. And then here we start messing with our training, test, and validation data. So we have the tokenizer with the out of vocabulary token set to on. We have here we fit our tokenizer on our text so that we have the length of well, we have all the unique words that's in our text. Then we transform our text to sequences right here. And we get some other info we need, like the vocab size, and we set our max length. Here we pad our sequences, so we are extending any sequences under 30 words to 30, and we are truncating anything past 30, just to have all of our data be the same size. And then we split our train and test data, and then we further split our train and validation data here. Okay. Then we defined a class and well, two classes rather. One was the one hot data generator function that was given to us through the announcements. Very useful this. It takes our data and batches and one hot encodes it so we don't run out of memory. And then here is a class given in one of the labs that stops the model training when we reach a certain percentage. I believe it's set to, yeah, it's set to 95%. All right, and then we compile our models. So here, I create a very simple model, just one simple RNN layer and then a dense layer. You can add dropout or L2 regularization as needed, and as well as mess with the learning rate. So just very simple model there to test out. And then I made a slightly more complex model, two simple RNN layers, still one dense layer before I compiled it. And then lastly, I made an even more complex model with four simple RNN layers and two dense layers before I compile it. So those were all of my different tests. Um, then, we one hot encode our training and validation data, and we fit our model here. Um, after we fit the model, we test it by one hot encoding our test data, and then we evaluate on that test data to get our test accuracy. And then lastly, we display the training validation loss as well as the training and validation accuracy in some beautiful graphs. Okay. Uh, I'll quickly go over the LSTM script. It's really just the same as the other one, except I've replaced all the LSTM layers with, or all the simple RNN layers with LSTM. So still got a simple model here that I was testing out. Still got a slightly more complex model here, and then an even more complex model right here. And then I, tweak all of the amounts of dropout layers and L2 regularization and learning rates from there. Okay, so on to the results. Starting with my simple RNN experiments with just one layer, one simple RNN layer and one dense layer. It seems like the model was so simple that it took a great many epochs before it was able to remember enough to overfit. Um, as we can see here, that it's 35 epochs, 35 epochs, 40 epochs, and having some data augmentation actually helped it remember a little bit more and kind of truncated the learning process. So the way I have this set up is the grabs over here are no data augmentation. These are going to be grabs with just dropout layers. These are grabs with only L2 regularization. And then I have a graph here for both data augmentation techniques. So the second model I made for simple RNN had two simple RNN layers and one dense layer. And this model was able to memorize data much, much quicker. So you see now we're at 95% accuracy at epoch 6, and having both data augmentation techniques helped it with the overfitting a little bit, lasted a few more epochs, but not much longer, it seems. And then for my complex simple RNN experiments, um, the performance, uh, it didn't really differ a whole lot from the moderate amount of layers in the previous slide. Um, Still same amount of accuracy, I'd say. Um, but in this one, data augmentation noticeably improved over fitting. We can see here in figures 3.1 and 3.5 that, we're hitting 95% accuracy at epoch 6, but when we start using both data augmentation techniques in 3.4 and 3.8, we're almost doubling our training time to like epoch 12 about. So data augmentation noticeably helped here. And then I experimented with the learning rates a little bit. I found that at a learning rate of zero point zero 0.01, the model couldn't really converge and the graphs looked pretty funky. At zero point zero zero 0.001, the model converged incredibly quickly in like 3 epochs, so it doesn't even really look like much. At 0.0001, uh, it converged and had the highest accuracy. And then at this incredibly low learning rate, in 5.4 and 5.8, we didn't really see an improvement in any accuracy, and it just took a very long time to converge. So not a noticeable improvement there. And here are all the test accuracies I got from my simple RNN experiments. The best model was the complex model with dropout layers, scored a 75%, 0.6 accuracy. And the best accuracy for the learning rates was 0.001. So, yeah. Okay, on to LSTM. With only one LSTM layer, one LSTM layer and one dense layer, the model still had difficulty learning with data, even with data augmentation. Um, learning, uh, and it I guess it was a little bit better than the simple RNN one, but it still like I had to cut off because it just reached the max epochs. It didn't really reach 95%. So data augmentation did help prevent overfitting on these graphs. With a slightly more complex model, I noticed that data augmentation didn't seem to have a noticeable effect. Like it's still, they all went a similar amount of epochs of around 20 or so, and the accuracies all kind of were about the same. So that was an uh, um, interesting feature there. And same with the more complex LSTM model, the data augmentation didn't seem to help a whole lot. I'm not quite sure why that was, but an interesting find nonetheless. Okay, and then while I experimented with my learning rates, similar story to the simple RNN, where at zero point zero 0.01 it kind of had trouble converging, whereas 0.001 it converged fairly quickly, and then 0.0001 we have a moderate amount of converging, but a pretty decent accuracy. Accuracy kind of suffered at 0.001 and lower. And then at this low learning rate, we don't see a huge improvement in accuracy, but it does take a very long time to converge. So it's almost not really worth it. Okay. And well, these are all the accuracies I got for all of my tests. We can see that the best model for LSTM was complex with L2 regularization only, and the best learning rate was 0.001. And in total, the LSTM slightly outperformed the simple RNN model. Data augmentation, we could see it really help with the simple RNN models, but we didn't quite see the same benefits in the LSTM models. So I thought that was interesting. And we also saw from our accuracy tables that the more complex models typically outperformed the simpler structures because I guess the simpler ones just weren't able to memorize a lot of the training data. So that is my homework 3. Thank you.